While surfing the internet, I recently stumbled across this picture of an image made out of intricate paper spirals glued together to form some sort of a mosaic. And my wife pointed out that this was called quilling and was an art form in itself. So I thought, why not try and rebuild this inside of Houdini? And when we look at how to form a paper spiral or how to define a paper spiral in Houdini, let's look at this schematic diagram of a paper spiral. And you can see that when forming these paper spirals, we have to take into account the thickness of the paper as drawn here. So when we look at a more arbitrary shape than a circle, we have to figure out how many turns of paper we can actually fill it with. So what this means in this case is we have to figure out the shortest distance of any point that lies on its border towards the center of the shape. And then we take this shortest distance that we found, in our case this distance here, and divide it by our paper thickness. And then we end up with a number of turns that we can fill this shape with. So in order to create a spiral, we have to generate new points forming that spiral. And the number of new points we'll be creating will be equal to the number of turns that we calculated here, times the number of points in the original shape here. However, we will not only copy those points, but we will connect them to form a proper spiral. But if we just connect the endpoints of these shapes, we will end up with a very weird looking spiral like this. So instead what we have to do is gradually move those points towards the center point. So for each newly generated point, we will have to calculate a vector pointing towards the center of the original shape, and then move each point a given amount into that direction. And the amount varies. We start with not moving the first point towards the center at all, until we gradually arrive at our last point of our newly generated spiral, which will move fully towards the center. So again, crappy spiral here, but this point will not be moved to the center at all, while this last point of the spiral will fully be moved, which should end up with a much nicer looking spiral than what I've drawn here. But the general idea is we will gradually move those points from 0 to all the way down to 1 in here. So let's build that. And in order to have something to work on, I found this nicely illustrated book at archive.org. It's called The Illustrated Book of Canaries and Cage Birds, and it's from 1878. Has some really nice illustrations, and I just took out this kingfisher here and in Photoshop just isolated him on a white background, and I also created this image just with a standard edge detection kernel. And of course you could do that in Houdini, I just opted to do it in Photoshop this time. But maybe a topic for another tutorial. In Houdini, we will start by dropping down a grid, diving in, and increasing the grid's resolution to say 1000 by 1000, because what we want to do is use the attrib from map to load our image onto that grid. Let's highlight this, let's invert the V coordinates here, and load up our kingfisher. And of course, as you can see, the kingfisher in German is called Eisvogel. Okay, that's the one image. Let's copy this node here and also load up the edge detection image, this one here. And I want to use this image to scatter points on the plane. And what I'm doing here is creating the initial shapes, the initial cells that we want to then turn into spirals. And I want to use our color as a density attribute, like this. So I now get points scattered along these edges here. And then I'm going to use the trusty old Voronoi fracture and duplicate this grid here. Dial down its resolution again to be only one polygon. And use these points here to fracture this grid. Like so. Now let's clean this up a bit and transfer back the color information on those individual Voronoi cells. Let's use an attrib. Transfer. Wire this in here, highlight it, and we can see this is a bit messed up. That is because we only want to transfer the color to the primitives and not to the individual points, which does not work, of course, because we do not have color on the primitives here. So let's use an attribute promote and promote the color from point to primitive and wire this in between here. And now we have our individual Voronoi cells colored in the colors of the image. What I want to do next is delete all the white cells here. I'm going to do that with a delete node, wire this in here, and I will delete primitives by an expression. And I'd like to check if the average color value, that means the average brightness, of a given cell is above a certain threshold. So what I'll do is I will add the individual color channels, then divide them by 3, and I'm going to check if that value is above 0.9, and then I will delete a cell, like so, before and after. Now let's reshape these cells to look a bit more round, more organic. I'm going to use 3 nodes here. First the resample, I'm going to resample to a length of 0.02. Then a smooth. And I want to smooth this a lot, so 50 iterations here. So let's highlight this, nothing much changed in here. So you can see a bit of those round edges appearing already. But when I smooth it, well, not much happening here actually. Oh yeah, let's set the constraint boundary to none. So now I got these more organic, more roundish looking cells here. And finally I want to resample this again. This time to a length of 0.01. Like so. Let's highlight the point display here. So I have a really dense point density here. Next, I want to store the center of each individual cell into an attribute. Let's do that with a primitive wrangle. Wire it up here, call it set center. And it's just a single line. Let's create a vector called CTR for center. And that's going to be equal to our current primitive position. That is the center of a primitive currently. So not much happening there. Let's just check. Just created this center vector here. Next, let's turn those closed shapes here into a line using the primitive sub. And under face and hull, I select to unroll the U, like so. Now what I'll have to do is find the minimum distance of any of those points to the center, like what we've been talking about in the beginning. And I'm going to use a prim wrangle again. Call this find minimum distance to center. Wire it up, and we're going to write a bit of VEX code in here, admittedly. So first, we want to know which points lie on this primitive. So let's create a new variable called npts, and it's going to be the prim points, which will return all the points that are in this primitive, coming in through the 0 input slot, and on our current prim number. Also, we want to know how many points those are, so let's create a variable called numpts, and it's going to be equal to the length of this array npts. So that's the number of points that we have on this primitive. Let's initialize our variable called minimum distance. And let's initialize it with something rather huge, like 1,000,000 or so. And now let's check for each point if its distance to the center of the primitive is smaller than our current minimum distance. So let's drop down a for each. And let's create a variable called npt, and in this variable we will iterate over all the points stored in the array npts, like so. Now that we will run through each point of the primitive, let's check for each point the distance to the center. So let's first get each individual point's position. Let's call it npos, and it will be the position of the point we are currently working on. Now let's calculate the distance. And it will be the distance from our primitive center to the point position. And finally, let's check if this newly calculated distance is smaller than the minimum distance. And if it is, let's set the minimum distance to the distance we just calculated. And finally, write out the minimum distance and the number of points. So let's create an attribute called dist. And it's going to be the minimum distance, and also an attribute, an integer in this case, called numpts for number of points in this primitives. And it's going to be equal to numpts, like so. Let's see if that works. Looks like it. We have a distance here, and we have the number of points. Now let's promote these attributes to the point. And we want to promote the attribute called dist from a primitive to a point. And we want to promote the minimum value, like so. Let's check in our geo spreadsheet under points. We have the distance written onto those points. Now, finally, we are ready to create those spirals. Again, with a primitive wrangle. Let's call this create spirals and wire it up. First, I want to specify how thick my paper will be. So let's call it width, and I'm going to drop down a slider called paper thickness. Let's create that slider, set it to something small, in our case like 0.002. And again, what we will need for this is we will need to know which points form a given primitive. So again, let's use our prim points function to extract all the points of an individual primitive here. And again, we will need the number of points, which again is the length of that array we just read out. Now let's calculate how many windings of paper we can fit into an individual primitive here, into an individual shape. So let's create an integer called max number of windings, and that will be equal to an integer value. And we will divide the distance attribute, that is the shortest distance from any point to the center, by our paper's thickness that's stored in the width. Now we know that how many windings we can put in there. Let's create a new primitive. And it should be a polyline, and this is where we'll store all our newly created points into. Let's set this primitive's color to our current primitive color, so the color gets transferred. Now, before we drop down a for each loop to create all those new points in our spiral, let's just create one more variable. Let's call it n. It's a counting variable. Should be a float. And let's initialize it with a 0. Now, as previously mentioned in a theoretical part, what we want to do is we want to create a maximum number of points here times the already existing points in our primitive. What we will drop down here is called a nested loop. So we will drop down a for loop, which will loop the maximum number of times that's stored in here. And then within that loop, we will call a for each loop, which will run through all these points stored in here. So let's create the for loop first. And inside that for loop, let's create the for each. And what we'll do once we run through each for each, and what we will do after we worked on a given point in the for each loop, we will increment our counting variable, the n. That's the last thing we will do in this loop, but it's very important that we drop it down. But the very first thing we will do in the for each is we will calculate the amount that we have to move a given point towards the center point. And let's call this offset amplitude, offset amp, like this. And it will be n, our counting variable, divided by our maximum number, that's the number of windings we will put down, times the number of points that we have in the primitive here. Next, let's get the position of our current point that we're working on. And finally calculate the offset. It means the vector pointing from our point's position to the center. Like so. Finally, let's move our point. So we now multiply this vector pointing towards the center times our amplitude that we calculated up here. Now that we have this new position, let's create a new point. And add it to our newly created primitive. And finally, after we've done that, let's remove the original primitive. That's this original shape here that we don't need anymore. And we want to delete its original points as well. Say 1. And we see that kind of did not work, so let's check out what went wrong here. And I think I found it. Up here where I calculate the maximum number of turns, I am referencing this dist attribute, which I promoted here from primitive to point, and while doing so deleted the original from the primitives, which I tried to access here. So let's uncheck this, and we see now we have those finely wound spirals down here. Save that. So let's highlight our point display again. And what I want to do is I want to resample these one more time, and this time use the resample to calculate the curve U attribute. And let's set it to resample to a segment length of 0.0025. Wire this up, highlight it, and we can see now we have a denser point density on the one hand. And on the other hand, when we go to the geo spreadsheet here, we have a curve U attribute. And the curve U attribute goes from 0 on the first point of a primitive to 1 on the last point of the primitive. Also, let's smooth this one more time with no constraint boundary and 24 iterations. What we want to do next is create a random z-scale to use that for extruding those spirals each individually. So again, primitive wrangle, call it set z-scale, and let's create the attribute called z-scale, and let's use a random function that we will fit. So first drop down the random function here, and we were going to use the prim number plus something as a seed, and let's remap this. So let's use a fit01 function because random goes from 0 to 1, and we want to remap it to go from 0.5 to say 1.5. So what I'm doing here is I'm going to generate a random number ranging from 0.5 to 1.5. I'm going to write that into an attribute called zscale. Now that I have that set, I'm going to use a polyextrude to extrude those individual spirals. And I'm going to use the point normal here, set an extrude distance of say 0.1, and under local control I will enable the distance scale, which is already set to my attribute called zscale. Let's wire this up, highlight it. That's going to take a bit. Let's zoom out a bit here. Well, it looks like the z-scale didn't work yet. That is because I set it on a primitive scale and I have to promote it to a point. So from primitive to point, z-scale, wire this in between here. And we can now see we have different extrusion heights. Next, what I want to do is move those center points of spirals a bit more upwards and add a bit of randomness to that, because that gives it really that organic look that reminds us of the handmade nature of quilling. And in order for that to work, I will drop down a connectivity sub first, which will give me a class attribute for each point that is connected to an individual spiral. Wire this up, highlight it, and after that I'm gonna drop down a point wrangle to move up those points, depending on their position on the spiral curve, and adding a bit of randomness. So let's call this maybe randomize Y position. And in here, first I will check so that we will only affect those points that have been extruded. And of course I could use a grouping here, but I will just check the Y position now. I can use groups, I can use whatever you like to check. For that, in my case, I'm just going to use an if statement here. So if my Y position is above, let's say something really small, 0.001, then let's read out our current point's position and store it in a vector. Like so. And now I will inline a bit, and I'm sure, and now I will inline a bit. And I am aware this might not be the cleanest way to write a code, but it can be very compact, and I will explain what I'll do here. So I want to set my position to a newly calculated position. On the one hand, I want to have this whole thing spiraling upwards a bit. So let's take care of that first. So I will create a new vector, which I'm going to do with a set command, and the position on the x and the z axis will remain the same. So pos.x, comma something for the y, and then pos.z. And now we will calculate this new y position. So let's add to the y position the curve attribute that we will in turn remap. So let's use a ramp, call this y remap, and let's use a curve u ranging from 0 to 1 depending on where on our spiral our point is. And let's maybe add a scaling factor, because otherwise those extrusions would get really big. So let's multiply this by something small, let's say 0.03. Let's create this and highlight our node. We can see now we have those slightly upward spirals. And again, I can change that amplitude in here, like so. And maybe let's create another slider for that. Let's call it Y amplitude. Add the slider in here and maybe dial it up to, 0.03. I like that. Okay. Now I've taken care of those inner points moving upwards, but I want to add a bit of randomness to it. So to this expression, I will add something, and I will add a noise. That is noise, not boys. And I will calculate the noise on a given position, and the position we'll be using, again, will be the curve u. But I want to increase the noise frequency, so let's multiply it by something, let's say 8. And also, in order to prevent the noise from being the same across the points in each individual primitive, I will add to it some offset, and I will use the connectivity information stored in the class attribute and multiply that by something bigger so I get real decent offsets. And finally, what I will do is I will remap the noise that I just generated to range from minus 0.025 to plus 0.025, which can be done by multiplying this whole result by 0.05. and then subtracting 0.025 from it. Wow, what an expression. Let's see if that worked. And we can now see we have those random bits, random offsets here, which really gives it this organic look. Now finally what I want to do is add a normal. And I can now take care of lighting, shading, and rendering this. So let's have a look at the tree. And it's a rather linear tree, which is kind of a standard looking tree when modeling inside of Houdini and not branching away too much. So what you can do now is add a bit of thickness to those spirals, maybe work a bit on those initial shapes though they don't intersect before creating the spirals and extruding them and doing all the modeling, and of course experiment with the generation of those initial shapes. I just used the standard Bernoulli fracture here. You can come up with all sorts of algorithms to generate those initial cell shapes and in turn generate a magnitude of beautiful patterns. So as always, hope you had fun with this. Looking forward to seeing the artwork you guys create with this, and it's cheers and goodbye.